Okay, so in today's class we will discuss about pseudorandomness. So the objectives of today's discussion will be on random bit generation. Then we will try to understand what is the notion behind pseudorandomness, and then follow it up with some statistical tests and also some idea about what is meant by cryptographically good pseudorandom bit generation. So we know pseudorandom bit generation to in context to various other fields in computer science like testing and so many other things, but we also try to understand what is the extra requirement for cryptographic purposes. Okay, so there is a requirement of unpredictability. Like for example, we have seen LFSRs. LFSRs are in general quite good good pseudorandom bit generators, but they are not so good for cryptographic purposes. Okay, and we have seen why, because they are quite predictable in nature. Okay, that is, given the sequence, we can again obtain back the given LFSR structure, and from there again regenerate the sequences. Okay, so usefulness in cryptography for pseudorandom, for randomness is actually enormous. So we have seen, like in context to one-time pads, the key stream, we have seen that the requirement essentially was randomness, right? So similarly, there are other applications like in generating the secret key for block ciphers, you would like to make it random. Okay. Similarly, we have not discussed till now in public key crypto systems, like for example RSA, we require to make some choices on prime numbers. Okay, so for example, primes P and Q are required. They are also supposed to be random. Okay, then in digital signature algorithms, the private key has to be also determined in a random fashion. Okay, so therefore the idea when I say that it is random means that they are supposed to be chosen from a space, and that space should be quite large. Okay, so that is one requirement. And the other thing is that the probability of a particular value being selected should be equal for any value. Okay, so therefore this is required because I do not want to, if there is a bias in the probability distribution, then any adversary can use this property to make an optimized search, right? So therefore he can target the search to a particular region, okay, of high probability. So therefore, in order to avoid such things, we would require a uniform probability distribution of all the values. Okay, so therefore these are the idea, requirements, and we have got a notion which is called true random bit generator. That is something which is called something like an ideal random number, okay, generator. So therefore, what is a random bit generator in an ideal case? It is a device which outputs a sequence of statistically independent and unbiased bits. So therefore, it's a device, suppose you can think of like a magic device which will output its bits which are which are statistically independent and they are uniformly chosen. So that is the idea. So therefore, if we have a random bit generator, so which means essentially that it's a device which will produce a sequence of bits, okay, all of which are which is essentially a random sequence. Okay, therefore the probability of any particular bit is uniform, and it's also unpredictable. That is, they are not correlated. Therefore, given a bit, the next bit should not be correlated depending upon the other bit. Okay, so you can actually use that to generate a random integer in this fashion. How? Now, because suppose I want a random integer in the closed interval from 0 to n, then what you can do is that you can do that by generating a random bit sequence of, say, ceil of log n plus 1. Okay, so many bits you generate, and then whatever sequence you get, you convert back into a random integer. Okay, so therefore, given a random bit generator, you can use that to produce random numbers, random integers. Okay, so ideally a true random number generator should be used, but the problem is that they are quite costly in nature and they are also inefficient. Okay, so therefore how we alleviate this problem is, instead of having something which is really true random, we try to substitute them by certain generators which are actually called pseudorandom generators. The idea is that the output of the random generator and the output of the pseudorandom generator should not be distinguishable to an efficient algorithm. Okay, so when I say efficient, I mean to say a polynomial time algorithm. Okay, because a polynomial means the input in this case is for example, the number of values being generated. Okay, so therefore the runtime should be polynomial, and such an adversary should not be able to distinguish between the output of this particular generator from that of a really true random generator's output. Okay, so that is the basic idea. So therefore pseudorandom bit generators are deterministic algorithms. So what does it mean? What does it mean when I say a deterministic algorithm? Each time you start with a particular starting point, it will produce you the same, it will give you the same result. Okay, so therefore it's a deterministic algorithm which, given a truly random binary, a truly random binary sequence of length k, outputs a binary sequence of length L which is much greater than k, okay, and which appears to be random. So the idea is that in case of a pseudorandom bit generator, there is a starting point of a small output, small random number, for example, which is of length k bits. Okay, so this is being, so suppose what you do is that ideally you use a true random bit generator, and from there you obtain a small k bit true random value. Okay, and now using that you try to generate a very large number of pseudorandom bits. The reason being, as I told you, that a true random generator is expensive and it is also inefficient, right? So therefore what I will do is that I will use it for generating small sequences, and then I will engage this true random generator's output by a deterministic algorithm to give me a larger sequence which looks random, okay, which appears to be random. So therefore the input to this particular pseudorandom bit generator is actually called a seed. Okay, and when we say that it is a deterministic algorithm, it means that each time you give the same seed, the same output generates. Okay, so therefore if you require to change the value, then you require to change the seed as well, right? So keeping the seed constant and trying it several times, it will still give you the same output. Okay, so it will really not be random in that case. Okay, so you need to change the seed also, and the output is called a pseudorandom bit sequence. Okay, so you see that this is actually not a fully random output, because you can easily figure it out. Why? Because in an ideal case, when you are generating a binary sequence of length L, then actually there are 2 to the power of L possibilities, right? But when you are using a k bit sequence to generate this, you see that out of these 2 to the power of L, you are actually generating only 2 power k, right? But still it should look random, which means that there should not be any polynomial time algorithm which is able to exploit this particular fact. Okay, so it's not actually random, but it should appear to be random, right? So therefore that is the basic notion behind a pseudorandom bit generator. So in order to evaluate whether a pseudorandom bit generator looks random, there are various tests which are being proposed. Okay, so these are called random tests, you can say. Okay, but the point is that the objective of all these tests is actually not to say that a binary sequence is random, okay, or pseudorandom, but the objective is to say that a binary sequence is not random. Okay, because you can do, say, n number of tests, and from there you can say that, okay, if it satisfies or it passes so many tests, then what you can say is that within these tests you have not been able to figure out that this is a weaker generator, okay, weak generator. But it doesn't nowhere mean that there can be another test, for which this particular sequence may fail, right? So therefore what you can say at best is that using so many tests, I have not been able to distinguish this output from a true random generator's output. Okay, so therefore this is a typical example which says that for example xn equal to a xn minus 1 plus b mod m. Okay, so therefore this is called a linear, this simple linear recurrence. Okay, so you see that if we keep the values of a and b and m secret, then you can start with a value of x0, which I call the seed, and you can keep on generating such sequences, right? So therefore you will see that if you obtain a fairly large number of outputs, that is xn values, then you can actually try to solve them and obtain the values of a, b and m, and once you are able to solve the values of a, b and m, this sequence generator becomes quite predictable, right? So therefore this sequence generator, you will see that for all the tests that we have seen, or rather that we will see, actually they will pass those tests. Okay, so therefore it will pass the standard random tests. Okay, but you still see that this is a not a very and it's not an unpredictable random generator, okay, and therefore such type of recurrence relations are not very much liked in the cryptographic community, okay, because they are quite predictable. Another example which we have already seen is the linear feedback shift registers, okay. So this is actually belongs to the same class, okay. So therefore we will try to understand what are the randomized tests, and also try to understand what are the extra requirements, okay. So in order to start that, what are tests, okay. So we will be talking about polynomial statistical tests, that is we will be talking about, we will try to understand that a pseudorandom bit generator is pseudorandom when a polynomial time statistical test or polynomial time algorithm works on the sequence, okay. So therefore given a pseudorandom bit generator and it produces a sequence, say S, okay. So the polynomial time algorithm will now act upon S and try to say that whether this is a pseudorandom sequence or not, okay. So we say that the pseudorandom bit generator is said to pass all polynomial time statistical tests if no polynomial time algorithm can correctly distinguish between an output sequence of the generator from that of a true random sequence of the same length, okay. So and with so therefore in a random case, for example, if I just tell you to, okay, distinguish this from this, what is the probability? If you are not given any information, it's half, okay. So if you are able to do this with a probability significantly greater than half, then it means that this output sequence generator is really not pseudorandom bit generator, okay. So therefore if you are able to distinguish correctly with a probability which is significantly greater than half, then we will say that this pseudorandom bit generator is actually not a good pseudorandom bit generator, okay. So therefore it should be close to half. So even if it is 0, then also it's bad, so it should be close to half, that's the idea. So it's the idea is similar to the idea of bias that we have. So you see that all these things are related actually, okay. And there is a test which is called the next bit test, which is as follows. It says that a pseudorandom bit generator is said to pass the next bit test if there is no polynomial time algorithm which on input of the first L sequence values, if I ask you to predict the L plus 1st bit, N plus first bit, okay, then your probability should also be close to half, okay, it should not be significantly greater than half. So that means that if I give you L number of values, from there you have to guess the next bit, okay, and the probability of this particular guessing should be also close to half. So this particular test is known as the next bit test, okay. So why we talk about the next bit test in particular is actually because it's a universal test. You can actually prove that it is a universal test, okay, but we will not prove that in this class. We actually have another semester course for this, so we discuss proofs of this type, okay, but in this class we will assume this fact that this next bit test is actually a universal test, okay. So the idea is that a pseudorandom bit generator passes the next bit test if and only if it passes all polynomial time statistical tests, okay. So a pseudorandom bit generator that passes the next bit test, possibly under some there are two possibilities, so anyway, possibly under some unproven, so it may be unproven, you can say, may be unproven but well known mathematical assumptions, is called cryptographically secured pseudorandom bit generator, okay. So therefore the universality means that if a particular pseudorandom bit generator passes a next bit test, then it is equivalent to saying that it actually passes all polynomial time tests, okay. So if you are able to prove this, then you can show that also, okay. So but the fact is that when you show that a pseudorandom bit generator passes the next bit test, it is typically under certain assumptions, okay. So these assumptions are actually some very well established sort of, it's not really proved, but these assumptions have stood for long periods of time, okay. So one example is factorization of numbers, factorization of integers into its prime numbers, okay. So if you take two very large numbers p and q, okay, and you multiply them and you obtain the value n. So the question is that you have to factor n into its prime numbers p and q. So this problem has actually not been shown to have any efficient algorithm till now, okay. So there are a lot of other examples of this nature, and these particular assumptions are being used to prove that a pseudorandom bit generator passes a next bit test, okay. And there are some quite theoretical constructions using these ideas, okay, but this is the basic notion behind it. So we will go into pseudorandom bit generator, but before that let us talk for some time on random bit generators, okay. So let us see some examples in hardware where you can actually generate random bits, okay. So for example, like the elapsed time between emission of particles during radioactive decay, okay, the thermal noise from a resistor or a diode, for example, the sounds from a microphone, gate delays in circuits. So these are some some type of phenomenon which are actually used to generate true random bits, okay. So the main idea is that they should not be deterministic, okay, they should be something like which is unpredictable, okay. And in software also there are certain things, like for example the system clock, like suddenly if I look into my system clock, it's something like a random number, okay. And the elapsed time between keystrokes or mouse movement, so when I am moving the mouse, when the keystrokes, okay, the user input, the system load in computers, the network statistics, these are some examples in software for true random bit generators, okay. But these outputs are not often really unbiased or not often really uncorrelated, okay. So it may happen that there is a finite correlation, there is a distinct correlation, there is a distinct bias. The bias means that the probability of a 0 being occurring is not exactly half, okay. It is something value p which is not equal to half, okay. So then there are certain extra steps that you have to do, right, in order to really obtain a true random bit output. So what you do is that you do some deskewing kind of operations, okay. So what is deskewing? So deskewing is, idea is that suppose there is a natural source of random bits, okay, and it's defective. So defective means that suppose it results in a probability of a 0 being occurring is some value of say p, okay, and p is not equal to half. So therefore the idea is, and also it may be correlated. Correlated means a particular bit depends upon the previous bit, okay. So then you have to engage certain techniques which are called deskewing techniques, which will take these defective bits and will give you a good a good sequence which is unbiased and which is uncorrelated, okay. So I can give you one possible example on this. So suppose there is a generator which produces uncorrelated but biased bits, okay. So uncorrelated means you know that the particular value does not depend upon the previous value, they are all independent, okay. So and the probability of a 1 is suppose p, and the probability of 0 is in that case 1 minus p, okay, and p is not half, okay. So p is unknown but it is fixed. So therefore suppose that I do not know what is the value of p, but p is fixed, okay, that is the assumption. So what you can do is that you can group the output sequences into pairs of bits, okay, and then whenever the output is 0 1, then you replace that with a 0, and when the output is 1 0, you replace that with 1, and rest of the cases you discard those bits, okay. So what is the probability of this event? It is p into 1 minus p, assuming that they are uncorrelated, okay. And what is the probability of this? It is also p into 1 minus p. So now you see that a probability of a 0 and a 1 are equal, okay. So that way you can correct and you can generate really good sequences, okay. So therefore you have now made them unbiased and also they are uncorrelated, right.
Does it not mean that p into 1 minus p equal to half?
P into 1 minus p is equal to half, yeah.
So we have fixed the value of p.
Yeah, p is fixed, p is unknown but it is fixed.
No, but if we say p into 1 minus p equal to half, then the value of p is known.
Yeah, but here there is a catch, because see there are certain values which you have already discarded, which you have thrown, okay. So therefore p into 1 minus p is not equal to half, right. because there are certain events. I mean, if you think of the universal set, then there are certain events like 0 being occurring, 1 being occurring, and nothing being occurring, right? So therefore, I mean, it's a very good question which he has asked actually. That is, what if p into 1 minus p is equal to half? Then actually there is a fixed value of p, right? So, but because of this particular event, it is not exactly equal to half. So therefore, p into 1 minus p is a constant. That is the main idea, because the main idea is that the probability of a 0 occurring and a 1 occurring are the same. That is the main thing. So there are some examples which we can learn from literature. These are very old examples, but I think we should a little bit study them because they are quite standard bit generator techniques. Okay, so FIPS is a body. Okay, FIPS is something which is called a Federal Information Processing Standard Body. Okay, so therefore this body gives you a lot of block cipher standards and sort of pseudorandom bit generation standards and things like that. So therefore this is a very old example of how a pseudorandom bit generation worked, and what they used in the underlying algorithm is the 3DES algorithm. So you know what is a 3DES algorithm? It's an encryption, decryption, encryption, right? Or so therefore you can use particular this algorithm in order to generate pseudorandom bit sequences. Okay, so how you do that? You take as an input a random secret 64-bit seed S, okay, integer n, and 3DES key k. Okay, so therefore these are your inputs to the algorithm, and what you output are essentially m pseudorandom 64-bit strings from x1 to xm. Okay, so therefore what you do is that you start like this. You take the date and time of your current event, and then what you do is that you apply your encryption algorithm ek and obtain a value I. Okay, and then what you do is that you take an XOR of I with your starting value of S, and you again apply your ek algorithm. So ek is your 3DES algorithm, and you obtain a value of xi, which is the next sequence value. Okay, and then you need to modify the value of S. So what you do is that you take xi, XOR that with I, okay, and then apply ek and obtain the next value of S, and you keep on repeating this for m times. Okay, and each time whatever value of xi you obtain, you are returning that sequence. Okay, so therefore the idea behind that is, and you can generalize this idea, this ek algorithm is actually use something which is called a one-way function. Okay, and there is a, so what is a one-way function? So one-way function are those kind of functions which are actually easy to compute, but they are hard to invert. Okay, so therefore in this case, if you don't know the value of, if you know the value of k, computing ek is quite easy. Okay, but if you don't know the value of k, then the assumption is that computing the inverse of this output is a hard problem. Okay, it's a difficult problem. So therefore what you do is that you take somehow you generate a sequence values like S1, S2 and so on, and whatever value you get for S, each time you apply the one-way function and obtain a sequence value. Okay, and that way you can export various bits. Okay, so for example here you take S, you are modifying S in the next iteration, and you are applying the one-way function and obtaining the next sequence value. So this is the idea. Okay, so you can generalize this into using other one-way functions also which are there in the literature, but this algorithm is quite central. Okay, it gives you the basic idea. Okay.
Means are we taking one string from the pseudorandom sequence and then using it to create seed for another sequence?
Yeah, I did not follow. Can you come again?
We have the sequence x1 to xm.
You have got the sequence x1 to xm.
The output is m pseudorandom 64-bit string.
Yeah, the output is x1 to xm.
Right. And now in the fourth point,
yeah,
we are producing that xi from the seed S.
We are producing xi from seed S. Yeah.
And in the next step, we are getting another seed from xi.
You are getting S for the next iteration.
Yeah. So the all this x1 to xm produced from different seeds, or
they are produced from different seeds, but the starting point of the seed is S. So after that you are modifying the seed value and generating subsequent values. Does that clear it? Okay. So there are some tests actually which we will see that there are 5 basic tests, okay, which a sequence is supposed to pass in order to sort of give a guarantee that whether it's actually not a random, it's a probable candidate of for a good pseudorandom bit generator. Okay. So what you do is that you take S, and suppose your S is equal to S0, S1 and so on till Sm. It's a binary sequence, and now you have to give some statistical test to determine whether the binary sequence possesses specific characteristics that a truly random sequence is likely to have. Okay. So there are some tests. I will quickly go into these tests because they are actually quite simple tests. One of them is called a frequency or a monobit test. So monobit test means that you determine the number of zeros and ones and they should be approximately the same. Okay. So these are some attributes for random bit generations, right, and your pseudorandom bit generation output also should closely match them, right. Otherwise any polynomial type algorithm will be just able to count out zeros and ones, and if they are different they will say that it's not a random sequence, right, it's not a good pseudorandom sequence's output, right. So it will be able to distinguish it from a random sequence, that's the idea. So therefore zeros, and this is a simple example. In the next case what you do is that you take a serial test where you take 2 bits like 0 0 0 1 1 0 and 1 1, and you count how many times these things occur, and they should also be same as that for a random sequence. Okay. So this is something which is called a serial test or a 2-bit test. Then you have got something which is called a poker test. So what you do is that you take your sequence S and you start dividing them into k non-overlapping parts, and each of them are of length m. Okay. So now you start counting that in a random sequence, so each of them is of length m, right. So how many possible values of each sequence are there? There are 2 power of m, right. So if you take m bit value, there are 2 power of m possibilities, right. So now you see that in a random sequence, what is the expected number of values of each m sequence, okay, m bit sequence, okay, and you see that in your output of your pseudorandom bit generator, probable pseudorandom bit generator, whether you get close to that, okay, and that way you can distinguish from a random sequence, okay, you just see that whether you can distinguish the sequence from a random sequence, okay. So therefore the poker test determines whether the number of times of occurrence of each possible 2 power of m subsequence is the same as that in a random sequence, okay. So this is a simple extension of the previous tests, okay. So then there is something which is called a runs test. So what is a run? So run means that a run of S is a subsequence of S consisting of, so run means like this, suppose you have got a sequence like 0 0, okay, and so on 0, and then you have got 1 1 1 1 1 1, like, so there are some values which are being held constant for a lot of times, and before that and after that that particular thing has never occurred, okay. So that is the idea behind a run. So therefore a run of S is a subsequence of S consisting of consecutive zeros and ones which is neither preceded nor succeeded by the same symbol, okay. So a run of 0 is something which is called a gap, and a run of 1 is called a block, okay. So what does a runs test do? So runs test also determines whether the number of runs of various lengths in the sequence S is as expected as that in a random sequence, okay. So then they do some expected calculations for random sequences and tests whether the number of times these runs occur, whether that is close to that of a random sequence, okay. So the tests are built upon some expected attributes on the random sequences, and then they check whether the pseudorandom bit sequence also satisfy those attributes, okay. That is the basic idea.
So how do you compute the expectation for a random sequence?
Yeah, that I have not told actually. So there are some, so for that you understand that you have to do a simple combinatorial analysis, right. So there are some equations for that, but I have not gone into those actually, okay. So you have to just assume that a 0 occurring is half and a 1 occurring is half, and based upon that you can do the enumerations, right. But this can be simple problems which you can expect in your examination, so that you can prepare. So in an autocorrelation test is also very simple. So the autocorrelation test is the test checks for correlation between the sequence S and non-cyclic shifted versions of it. So we have already seen an autocorrelation. So autocorrelation means you test a sequence S, and then you see that consider the shifts of that particular sequence, and you see that how many times they match. Okay. So this we have seen in our correlation attack test also. It's something similar. Only autocorrelation means with the same sequence, right, with itself, right? How many times there are coincidences. So that also should be matching that for for what is again you calculate the same quantity for a random sequence, and you see that whether it matches with your pseudorandom bit sequence. Okay. So that is the idea of autocorrelation test, but all these tests are actually done using some idea which is there in probability or statistics, which is called hypothesis testing. Okay. So for example, the number of zeros and ones will not be exactly equal, right? So how much do you allow the tolerance? Okay. So therefore there will be ideas which are like something which is called you have to use principles of the something which is called probability density function or PDFs, okay, and how they are being used to calculate something which is called hypothesis testing. So therefore you make certain hypothesis and then you test whether this hypothesis hold or not. Okay. So for that you have to make certain assumptions, that is whether a random sequence, given a random sequence, what distributions do they follow. Okay. So in statistics there are certain very standard distributions, like for example there is something which is called a normal distribution, there is something which is called a chi-square distribution, and things like that. Okay. So therefore you will assume that a random sequence maybe follows a normal distribution, and then based upon that you will make certain hypothesis, and you will check whether the computed values for a particular sequence are satisfying that which it should for a normal distribution. Okay. So for example, let us consider what a normal distribution look. I think many of us know what is a normal distribution, but this is roughly the idea. A variable x has a normal distribution with mean mu and variance sigma square if the probability density function follows this equation. So I hope that all of us know what is a probability density function, right? So I will just briefly say that in case of discrete probability computations, each event has got a probability, but in a density function, probability density function, there is a function associated. Okay. So every event does not have a probability, but intervals have probabilities. Okay. So therefore you do not do a sigma, but you do an integration. So therefore this function should be an integrable function. Okay. So therefore the idea is that you can actually, in a case of a normal distribution, you can enumerate each value of fx as by this quite simple looking equation. Okay. And then you can obtain what is called a normal distribution with mean mu and variance sigma square. Okay. You can actually standardize this, normalize this, and you obtain something which is called n01. Okay. And a normal distribution will look typically like this, right? So you see that there are certain values which are being specified here, like for example alpha being equal to 0.1, 0.05 and so on, and then you have got certain x associated. Okay. So what is the idea? The idea is that, let us take this for example, it means that whenever your x is greater than 1.6449, okay, then the probability that you have got, how many values you have got beyond that range, is actually 5%. Okay. So therefore out of all these values, only 5% values are actually lying outside this range, that is they are greater than x, they are greater than 1.6449. Okay. So therefore why are these values useful? The values are useful is because of this fact, that is I can expect, for suppose for a particular sequence, if I say that okay, I expect the value of a particular thing which I am counting, for example, is that suppose I want to compute the number of zeros and ones, and I want to compute the difference of numbers of zeros and ones. Okay. So then the idea is that the number of zeros and ones should be very small, right? So they should not lie beyond a region. Okay. So what region? So suppose I say that okay, they should not be more than 1.6449. So that means that for 5% of the cases there is an expectation that a good value which is still following the normal distribution are actually discarded by this test. Okay. So but The thing is that whether this 5% is tolerable or not, that depends upon my requirements. Okay, if I say that okay it's not tolerable, then I will say that okay 2.5%. In that case, I will look for values which are beyond 1.966, right? But there are issues. For example, I will come to them in details. So this is the basic idea of a normal distribution. Similarly, you have something which is called a chi-square distribution also. Okay, so chi-square distribution looks like this. So you don't require to commit these equations or things like that, but the main idea is important. So therefore, try to understand the basic principle. Okay, so therefore, in case of a chi-square distribution, a random variable x has a chi-square distribution if the probability density function is defined like this. Okay, and I'm not going into the details, but the thing is that there are, I don't think that it is visible very much, but therefore I have read this value. Like for example, if I read one of the rows, then you have got values like this. Suppose v is equal to 5 and v is an integer, and then like the normal distribution we have values like alpha equal to 0.025 and x alpha is equal to 12.8325. Okay, so it means that if your probability of x is greater than x alpha, then that value is equal to alpha. Okay, so therefore there is a chance that in 2.5% of the cases your x is actually greater than alpha. Okay, x is greater than x alpha. So what I can do is that I compute the value of x, okay, which is my intended value, okay, and that is something sometimes called a statistic. Okay, so I compute the value of x and I check that whether x is greater than x alpha. If x is greater than x alpha, then I discard that value. I say that it's a bad value. Okay, but there is a problem. You see that there can be an error, because you see that in 2.5% of the cases there is a probability that is actually good. Okay, but I'm still discarding them. So these kind of errors are called type 1 errors. Okay, then if you see the type 1 errors, immediately you can think that there is something which is called a type 2 error, which says that I accept something and it is bad. Okay, so these are common techniques which are being used for hypothesis testing. So therefore in general, a hypothesis is an assertion about a distribution of one or more random variables. In our case, we will make an hypothesis like, for example, I say that a given pseudorandom bit sequence generator's output is actually a good pseudorandom bit generator. That's my hypothesis, right? So therefore what I do is that, you see that this is not a very deterministic way of testing, it's a probabilistic way of testing, which means my testing principle can fail. So there are errors, okay, and so the value alpha that we said is actually quite important, because it determines whether I am giving priority to my type 1 error or type 2 error. Okay, so just try to understand the basic principle. Okay, so the reason why I said is that we should understand the basic principle, but the formula and equations we can always follow. We can always see them. Okay, so that is, but try to understand the basic principle of how a random test works. Okay, so as I told you that a statistic is a function of the elements of a random samples. For example, the number of zeros in a sequence. Okay, so suppose I am in a given sequence of length n, I am starting to compute the number of zeros. Okay, so in that case, this gives me the value of x that I was talking in context to the distributions. Okay, so that x is my statistic. Note that it is not statistics. Okay, it's statistic only. Okay, so therefore there is a slight distinction between what I say as normal statistics and this particular statistic word. Okay, so it is assumed that a random distribution is either a normal or a chi-square for a value of v, and then what we do is that a significance level alpha is chosen and a value of x alpha is fixed. Then you compute the value of the statistic, for example the number of zeros, and then the statistic expected to, suppose there can be two cases. The statistic is expected to take on smaller values. This can happen, like for example I say the difference of number of zeros and ones, that statistic was supposed to take a very small value. Okay, in that case, if the statistic excess, for example that is my computed value of the statistic, that is greater than x alpha, then I reject that. Okay, so this is sometimes called a one-sided test. Okay, but there can be some examples where actually the statistic is expected to take intermediate values, that is neither very high nor very low. In that case, I will check whether xs is greater than x alpha or when xs is less than minus x alpha. In both the cases I reject. Okay, so these are called two-sided tests. Can you give an example of this among the 5 tests that I told? I can give you, you can go back and see what are the 5 tests. So one, you had a frequency test, you had a serial test, you had a poker test, you had a runs test, you had an autocorrelation test, and that's it. So these are the 5 tests that you had. So which of them do you think should have an intermediate value? Yeah? Your autocorrelation test. Okay, so it should not be, if you compute the autocorrelation, it should not be actually very much correlated or totally uncorrelated. Totally uncorrelated means you can flip and you can still obtain the same thing, right? So suppose there is a 1-0 sequence and in all the cases there is a mismatch. Okay, so then you see that is also not very much desirable, right? So therefore you would like an intermediate value for that. Okay. So that is a basic idea. So now we will just conclude our talk with this. So let's see an example. So of all the 5 tests, have got a corresponding statistic which I have not told you actually, but for example for the frequency test, the statistic which is generally used is this equation, n0 minus n1 whole square by n, where n0 and n1 are, you understand, the number of zeros and number of ones, okay, and n is the total size of the sequence. So the expected value of this statistic should be low. So therefore what type of test do? You do a one-sided test. Okay, so you see that whether xs is greater than x alpha for a given choice of alpha, and if it's so, then you discard that sequence. Okay, that is the way how all the tests are also being defined. Okay, but I really don't want to go into this, but I will conclude with 2 pseudorandom bit generators. Okay, one of them is called the RSA bit pseudorandom bit generator, and the idea, I think we will not be able really to appreciate at this point because we really have not studied RSA, but just let's see the running of the algorithm. It says that what you do is that you generate 2 large prime numbers p and q, and then you compute something which is called n equal to p into q, okay, and compute something which is called phi. So I think we have seen phi, right? So what is a phi? Yeah, but what is the name? It's called the Euler-Toscan function, right? So phi is equal to p minus 1 into q minus 1, and then what you do is that you select a random integer e such that e is co-prime to phi, okay, and then what you do is that you select a random integer x naught in the closed interval 1 to n minus 1, and then you repeat this procedure. So what is the procedure? You start with the value of xi, you compute the power of, when you raise it to the power of e, and then you take a modulo n, and each time you export the LSB of xi, okay, and that way you can create one sequence. So these are actually quite commonly used pseudorandom bit generators, and you can actually show that the idea, or rather the assumption is that this is a good pseudorandom bit sequence generator if solving the RSA problem is hard. Okay, so you can actually show the equivalence. Okay, but this is the basic idea. So the basic idea is that you take a value of seed and then you raise it to the power of say e, and then you take a modulo n operation, and each time whatever value you are getting, you are just exporting the least significant bit of that. Okay, so that way you can generate, and there is another example which has got a quite funny name. It's called the Blum Shub generator, or the Blum Shub generator. So it's also very popular generator. It's called BBS generator. So it says that you generate 2 large secret randoms and distinct prime values p and q, each congruent to 3 mod 4. Okay, so then what you do is that you compute n equal to p into q, and in the previous case you were computing the powers of e, right, but in this case you start squaring. So you take xi, x0 for example, you make the square, you get x1s, okay, and then you each time you are again exporting the LSP. Okay, so this is also based upon the problem that if factorization of n is a hard problem, then this should be a good pseudorandom bit generator. So that is the idea. So you see that these class of generators are based upon the fact that certain problems in mathematics are hard. Okay, so we have really not seen such kind of problems in depth. Okay, but when we go into RSA and when we go ahead, and that is when we go to asymmetric cryptography, then we will discuss this in quite details. Okay.
What do you mean by like it is hard? Just because we can always do it O n time.
Yeah, of course. So okay, so as I told you, when I talk about efficiency, I am talking about a polynomial time algorithm. Okay, so Polynomial time is input size. Okay, so therefore, suppose I tell you that whether a number is prime or not. Okay, although there is now a polynomial time algorithm to determine whether a number is prime or not. In typical case, what we will do, we will start taking its factor till square root of n. We will just keep on dividing and check whether it's a factor or not. So what is the runtime of your algorithm? It's O root n, right? But in this case, this n is not your input to the problem. So if you, I think you are doing an algorithms course, right? So therefore, in this case, what is the input to your problem? The input is the bit size. Okay. So in terms of the bit size, okay, this problem is actually exponential problem, because given, say, I mean, if your bit size is, for example, small n, then the number is actually 2 power of n, right? So therefore, it's actually an exponential algorithm in terms of the bit size. Okay. So therefore, factorization in general should be a hard problem. That is the assumption, but there is no proof why it's a hard problem. Okay. So whenever we say a problem is hard, it means with respect to its input size. That is most important, right? So when you are talking about sorting n numbers, then it's the number of integers that you are sorting, that is the input to your problem, right? But when you are factoring a number, then it is, or rather when you are saying that whether a number is prime or not, then it is the bit size which is the input to your problem. Okay. So you have to first of all understand what is the input size of the problem, and then according to that you will talk about its complexity, right? So therefore you can ponder upon certain points, like we have discussed about the Fistel cipher, like we have discussed about the Fistel structure. Then you can just think on that whether one round of this structure or 2 rounds of this structure is pseudorandom or not. It is actually not pseudorandom, and actually there are proofs which says that there are quite involved proofs which says that the 4 rounds of Fistel structures are actually good pseudorandom bit generators. Okay. So there is a proof which is called based on something which is called a Luby-Rakov construction, but we will not go into those in this class, but you can discuss, just think on these problems. Okay. But this is quite simple, you can easily figure out why. So this is the book that I have followed by Menezes. You can go through this book, and next day we will start with the topic on cryptographic hash functions.